Alright, so let's start with just the inverse of a function in its most basic form. So here we have a set of ordered pairs. 3, 1, 4, -1, 6, 2, -3, 4. You could graph a function on the xy plane pretty easily. Right 3, up 1 would be here, etc. So inverse of this function is simply this. First off, it's listed as, so that means that's the symbols for the inverse of the function g. And all you do to find the inverse is swap your domain and range. So the inverse of this function would be 1, 3, -1, 4, 2, 6, and 4, 4, -3. Kind of ran off the screen a little. I'll move it over. And so, now let me fix that. That's pretty ugly. Kind of ran out of room there. Okay, so that's it. That is the inverse at g at x. And ultimately, you could do that with almost every function, finding its inverse. Now, there's going to be some issue on once you invert it, is it a function? We're going to talk about that maybe in another video, but essentially that is it. If you can flip the points around, you know what an inverse is. So what happens if it's not listed as a set of ordered pairs? For instance, 2x plus 3. Well, get a set of pairs. So make a table. So here's x, here's y. Maybe I'm going to pick 0, 1, 2, and 3 because I'm unimaginative. So if I plug 0 in, that would be 2 times 0 plus 3, or 3. 5, see 7, and 3, 6, 9. And so I know the inverse at x would be then, if you flopped those around, would be 3, 0, 5, 1, 7, 2, and 9, 3. Okay, just a simple matter of calculating a new equation for this. Well, this is a linear equation. If you think back to your y equals mx plus b days, so we start with finding your slope, and so I'll just, let's just use these 2 points right here. So slope m is y2 minus y1 over x2 minus x1. So in our case, it would be 0 minus 1 over 3 minus 5, because that's the direction I chose. So that'd be -1 over -2, or 1/2. Okay. So far we know we have the equation, and let me just keep on rolling down here. So far we know we have the equation y equals 1/2 x plus b. So we still have that b to contend with. And so what we do then is pick one of those 2 points. I'm going to pick the 3, 0. So 3 equals, oops, sorry, wrong way. 0 equals, 0 equals 1/2 times 3 plus b, if you plug it into the correctly. And so I would know 0 equals 3/2 plus b, so b is equal to -3/2. So we've got our inverse function. There's lots of different algorithms for calculating it, and so f inverse of x would equal 1/2 x minus 3/2. So there's one way to do it. I mean, using some of the skills hopefully that you already have. Okay, so these two are inverse functions of each other, unless I made an error. Now, Another way to do that would be just simply to use Geogebra. And I just wanted to show you kind of what these um, two graphs, whoops, hitting the wrong one, whoops, here. Alright, so I'll just shrink it up here. There we go. Alright, so what do these two graphs kind of look like? So we go ahead and plug those in. I'm going to hit pause for just a second. Alright, so what I did is I went ahead and graphed these both in Geogebra. Stuck it in the input value here, right there. And here was our original, 2x plus 3. And then our second one was 0.5x minus, our inverse function was 0.5x minus 1.5, or 1/2 x minus 3.5. And you can take a look at the equation here that we have. What's kind of interesting about it is that it looks pretty symmetric. And in fact, it's symmetric about the line y equals x. So I'll type that into the equation as well. And there it is. So, and you can kind of see that symmetry forming. And that symmetry is true for all functions in their inverse. They will all be symmetric around the line, about the line y equals x. So that's kind of why I threw that in there. And so GeoGebra is pretty powerful to help us visualize that. Okay, so the other thing you can do is you can use composition of inverse function property to see if they're truly inverses of each other. And basically what that is if you compose the function and its inverse at x, you should end up with x. And likewise, if you compose the inverse and the original, you should also end up with x. So, and all those f's kind of get confusing. So let's just call one of them g at x, and we'll just use our original one, 2x plus 3, and we'll call the other one h at x, which was 1/2 x minus 3/2. And so you just compose those to verify. So if f at g at x ends up being x, or not f, excuse me, h, because I used the letter h. H at g at x equals x, and g at h of x equals x, then we know the two are inverses. Well, I've already determined that, but we'll show you how you can do this symbolically as well. So to compose this, you start with g. So this would be h at 2x plus 3. That goes in place of the g right here. And then you take the 2x plus 3 and plug it in to the h function. So that would equal, I'll go down here, 1/2 times 2x plus 3 minus 3/2. And go ahead and keep simplifying. And if you distribute, you'd have x plus 3/2 minus 3/2, and 3/2 minus 3/2 is x. And so we know that on that, at least in that case, it's equal to x. Now let's go the other direction. So the other direction is h. You start with h at x. So g at h at x is 1/2 x minus 3/2. And so you plug that into the g function. So you'd have 2 parenthesis 1/2 x minus 3/2 plus 3. And you can probably already see what's going to happen here. So that'd be x minus, if you distribute the 2 through, x minus 3 plus 3, and that is also x. So that also verifies that they're inverses of each other. And that's where I'm going to stop for the first video. I've got more to come. But good luck. I hope this helps, and see you next time.